When you step onto a scale, does it measure your true weight or your apparent weight? Let's take a look. So first, let's create a scenario so we can analyze what it looks like with having no acceleration. And this is going to be the same scenario as if you were walking onto and stepping onto your scale in your bathroom. Let's just take this scale and place it on an elevator, as it'll help us to analyze and understand how apparent weight actually works. So when you go to step onto the scale in the elevator on the ground floor, you have an acceleration of 0. The cart is not trying to accelerate your mass in any way, shape, or form because you're not moving. And this is also true when you have a constant velocity. So when you first get onto it and while you're moving at a constant velocity in between floors, your acceleration is 0. Okay, the way the elevator works is that you typically would get on, it would cause an acceleration, reach its maximum speed, maintain that constant velocity, and then accelerate in the opposite direction to slow down to let you off at the floor that you require. So let's look at the forces. So from a free body diagram standpoint, we have the force of gravity that is acting straight down, and the force of gravity is equal to the weight. In this case, the weight is 820 newtons. Additionally, we have the normal force. This is the scale pushing back on the feet of the person that's standing on the scale. Now, when we're analyzing it from Newton's second law, we find that the sum of the forces in the vertical is equal to the normal force minus the force due to gravity, which is equal to the mass times the acceleration in the y direction. Rearranging this equation, we find that the normal force is equal to the force of gravity plus the mass times the acceleration in the y direction. Now, the force normal is what we're referring to as the apparent weight, and your force due to gravity, which is actually your true weight. Okay? When you're stepping on that scale, what you're actually reading is how hard the scale is pushing back on your feet. That's really what it's measuring. It's measuring your apparent weight. However, when we find that the acceleration in the y is actually 0, then the only thing left is that the force normal is equal to the force of gravity. The whole mass times acceleration goes away. And so with 0 acceleration, the scale is actually reading your apparent weight, which is equal to your true weight, as you can see, 820 newtons. Well, what happens when there's a positive acceleration? That scenario that I just was describing, where after you get onto the elevator, you're at the ground floor, and it has an acceleration in the positive direction. It's going to take you up to whatever floor you're going to. This also is the case when you're actually traveling down with a negative velocity and the elevator slows down to stop you at the floor that you need to get off. In either case, you have a positive upward acceleration, and if you've ever, you've certainly been in an elevator, if you've experienced this, you realize that you feel this push down, like you feel a little heavier. You might even feel a little bit of buckle in your knee from that acceleration, which is an acceleration in the positive direction. So looking at the forces, we still have the force of gravity, your true weight, which is 820 newtons. There is a normal force. In fact, this normal force, we know to have a positive acceleration in our understanding of Newton's second law that I have to have an imbalance of forces in the positive direction to cause an acceleration in the positive direction. Well, it's really this normal force is the scale pushing you onto your feet. It's not only fighting or working against the force of gravity to support it, it actually has to cause enough force to accelerate you in the positive direction. So summing up the forces, again, we have the same equation for our apparent weight, which is just a rearrangement of Newton's second law. And what we find here is that this mass times acceleration, if I have a positive acceleration in the y direction, I'm going to add the mass times that acceleration, adding that to my force of gravity, my true weight, so that my apparent weight, whenever I have a positive acceleration, is always going to be greater than my true weight, or the normal force is going to be greater than the force of gravity. Well, what is the case on a negative acceleration? Well, in a negative acceleration in an elevator, if you think about it, there's a couple scenarios where that could occur. You're already at the top floor that you are getting onto the elevator, and you have to go all the way down to the ground floor or some lower floor. You're not moving, and then as soon as the cart starts to move in a negative direction, you have a negative acceleration. So it has to go from zero velocity to its maximum velocity. And during that period where it's changing its velocity, that has a negative acceleration. And the same is also true when we look at traveling upward. Right before we're about to reach our top floor, we need to slow down. And so in doing so, we have a negative acceleration. In either case, your inertia either wants to stay at rest, in the case where it was at a higher floor and going lower, or it wants to keep moving up. When you have a positive velocity and the cart starts to slow down, you feel yourself start to surge up a little bit, and that's your inertia. That means there's less force on the scale, so your normal force is going to be less. So again, looking at the free body diagram, your force of gravity is still there. The normal force is still there, but it's to a lesser degree. If we look at the equation now, in the acceleration, we have a negative acceleration in the y direction. And so when you carry that negative through, you can see that the mass times your mass times the acceleration you're experiencing is going to be subtracted from your true weight, or taking it away from your force of gravity. And so the apparent weight is always going to be less than the force of gravity, or your true weight, whenever you have a negative acceleration. In this case, we're showing a 600 newtons on the scale with the negative acceleration that we were experiencing. Well, what happens when that negative acceleration grows? Let's just say, for example, that this is just a thought experiment, but if the cables were cut from your elevator, what would happen? Now, there's emergency braking systems, but let's just assume that the whole elevator cart is in free fall condition. So it's accelerating to the earth at negative g, or g in the negative direction. What would that mean in terms of the normal force, or this apparent weight, reading on the scale? Well, you still have the force of gravity acting on you, right? That didn't go away. The gravitational force field is pulling down on you. In fact, it's also pulling down on the cart, which is why it has an acceleration of g, hurling down towards the center of the earth. Well, let's look what it does to the normal force. So again, we go back to our equation. Everything here is still the same. But now for that acceleration in the y direction, we're not just going to make it a negative, we're going to actually make it a negative g. And then by pulling out the mass, we can see that we have the mg for the force of gravity plus mass times the acceleration in the y, which is negative g. Pulling the mass out, we end up with g minus g, or 0. So the mass times the 0 is going to give us 0 newtons. So the normal force, as you can see on the scale reading 0 newtons, for an object that's in free fall inside of another object that is also experiencing free fall, is not going to be able to provide a support force. There's no way that the scale can actually support your weight to get a reading. The elevator cart, the scale, everything is accelerating at the same rate, and therefore there is no reading on the scale. This is what we call apparent weightlessness. In fact, this is how astronauts will train. They can take airplanes up to the outer reaches of our atmosphere and then let the plane free fall back down, and inside the cargo bay they get to experience what it feels like to be a weightlessness, or apparent weightlessness. And this is true of the astronauts in the space station as well. It's not that there's no force of gravity acting on the astronauts as they orbit the Earth. It's just that they are experiencing the same acceleration as the space station. And so when you're experiencing the same acceleration as the surrounding objects, you have this sense of apparent weightlessness. Thank you, and I'll see you soon.